11.6, making decisions and predictions. I can use probability to make decisions and make predictions.
Thank you, Luke. We can use probability to make decisions and predictions, and let's talk about how. Last week, there was a person standing outside of Target in Eden Prairie, and they were asking people what they thought of their experience inside Target. They asked 500 people in total. 125 of them said, wow, I was really pleased with how things went in there. 340 said, no big deal. It was just an average experience, not good. Not bad, I mean. It was pretty good. It was okay. And 35 people were smoking mad. They're like, oh, that was awful. They were unhappy. Target then took that data and said, wow, if we have 35 unhappy people out of 500 in Eden Prairie, I wonder how many unhappy people we have out of 500,000, because that's about how many customers go through our doors every day. So they figured that out by probably plugging it into a computer, but their computers went down, so they used actual math, right? And the actual math is what's used to make the computer programs. So they wrote a, and they knew that in Eden Prairie, how many were unhappy? And how many did they ask? And they wanted to know how many were unhappy. Look how we're lining up the labels, right? Out of how many? Out of how many, though? 500,000. How do you get from 500 to 500,000? So what do you do at the top? And we found out that how many customers were unhappy? 35,000. Excellent. I don't know if you remember this one or not. It was a couple of weeks ago because of spring break, but Joe was bored one day, and he wanted to figure out how many times he could accurately predict the card he was going to draw if he did it 1,000 times. So a deck of cards has how many cards? 52. Joe would get it right approximately 1 out of every 52 times then, right? Yeah. Theoretically speaking. So if he did this 1,000 times, he just lined up his labels, did he not? Yeah. And 52 to 1,000, it looks like is what? 19. What? 19.23 rounded, so we multiply 1 by 19.23, and we said Joe is approximately going to predict correctly his card 19 times. Does everybody remember what the squiggly equal sign means? Yeah. What's it mean again? Oh, good, I just said that. The last one then, Tori and Abby were flipping a coin. Tori wins if exactly one coin lands heads. Abby wins if not. Remember, most of you said that this was an unfair game, right? I think all but 2 groups said it was an unfair game. But then when we actually showed our work, hint, hint, show your work, right? Draw a picture, make a tree diagram, we found out that actually the game is fair. Abby would win in these 2 situations. I'm sorry. Abby would win in this situation and this situation, right? And Tori would win in this situation and this situation. So there were only 4 situations. Tori won 2 of them and Abby won 2 of them, right? Is it a fair game? Yes. Is it important that you show your work even if you're certain on what the answer is? Yes. We proved that to you, correct? Yes. Good. And then down here, Abby's a poor loser. She changed the rules. We used the exact same tree diagram because you just basically do the same thing. Actually, did we use the same tree diagram? Yes. Where did we put it, though?
We used it. You just use that one. You just use that one.
Oh, yeah, we redid it. Okay, I got you. Because I think it was exactly 1 had to be heads, right? No. What was the rules? I should probably read it. She said if at least 1 coin lands heads, she will win, right? So in this situation, is she going to win? No. No. Is Abby gonna win here? Yeah. So this is Abby, this was Tori. Is Abby gonna win here? Yeah. Is Abby gonna win here? Yeah. So Abby's gonna win 3 out of every 4 times, right? The moral of the story for this fair game coin flipping thing is draw a picture, make a tree diagram, right? Yeah.